Hi everyone, my name is Suraj, and today we're going to be walking through discussion 9 from the fall 2019 iteration of Data 100. Let's get into it. So in this first problem, we're given 5 different terms that relate to our least squares problem setup, and we're also given this nice picture, and we're asked to match these terms to the picture. Okay, so before doing that, what I want to do is sort of outline a toy model that will help us in defining what each of these terms mean, and then I'll elaborate a little bit more about how exactly we can interpret this X matrix. Okay, so suppose the model that I want to sort of fit is that I want to be able to predict people's weight given their age and their height. Okay, so I go out in the real world, collect a lot of people's age, height, and weight, and now I want to try and see if I can model the relationship between age, height, and weight. Specifically, I want to predict weight given age and height. Okay, so maybe my model will look something like predicted weight, so I'll say weight hat is equal to some constant term plus some constant times people's age plus some constant times people's height. Okay, so I've gone out in the real world, collected age, height, and weight. This is the model that I want to try and fit, right? So my goal is to try and figure out what the values of these betas are. And so now in creating my X matrix or my design matrix, I'll have 3 columns, right? Because I have 3 features. One, which I'm sort of implicitly multiplying by beta naught here, is a column of all ones. Okay, and so that will allow me to have this intercept or bias term beta naught. My next column will be a column of everyone's age, so age 1, age 2, so on and so forth, till age n, right? Because I have n observations. And my third column will be everyone's height. So height 1, height 2, so on and so forth until height n. Okay? So the main reason for me doing this example is to illustrate the fact that each column in my data matrix corresponds to a single feature for all of the observations. Okay? So for example, the first column in X is just 1 for everyone. The second column in X is everyone's height. And third column in X is everyone's weight. The rows in X then are all of the features for one observation. Okay, so the first row is the age, height, and intercept term for one person, right? The second row is the age, height, and intercept term for the second observation, so on and so forth. So columns represent one feature, all of the observations. Rows represent one observation, all of the features. So we can interpret this data matrix X as consisting of 3 column vectors or feature vectors, okay, which I'll write as x1, x2, and x3. That's an ugly arrow, x3. Okay, and so this interpretation will be helpful for us while working through this geometry of least squares problem. Okay, so before we start matching terms to this diagram, the last thing I want to do is define exactly what the span of X is. Okay, the span of a matrix can be thought of as the set of all vectors you can reach by taking linear combinations of the columns of that matrix. In this case, our matrix is X, and so the columns of X are these vectors x1, x2, and x3, or in general, x1 ... through x sub p. And so this is the set of all linear combinations of the columns of X. And so this we can think of this as being the set of all vectors of the form v1 x1 plus v2 x2 plus v3 x3, where v1 and v2 and v3 are all scalars. Okay, x1, 2, and 3 here are vectors, v1, 2, and 3 here are scalars, and so the result of this linear combination is another vector. So it's the set of all vectors of this form. Another way to express this set, though, is just as the set of all vectors x times v, where v itself is also another vector. Okay, so in this first interpretation over here, I'm saying v1, 2, and 3 are all scalars, and I have 3 of them. Over here, I'm just packaging v1, 2, and 3 into its own vector of 3 elements, hence the 3 over here, and I'm saying the span of X is the set of all resulting vectors when I take X and multiply it by a vector on the right. Okay, so the span of X is a set of all resulting vectors from this matrix multiplication. Okay, so anytime in the options that we look at, we see x times some vector, we know that that's just another vector in the span of x. Okay, so hopefully that illustration helped. I'll remove this to save space, but you can screenshot it if it helps. Okay, and so now filling in this picture, we see that there's 5 options and 4 of them look like vectors and 1 of them doesn't look like a vector. And so the only one that's not a vector is the span of x. Okay, because the span of x isn't a vector, it's a set of vectors. Okay, it's a set of all vectors you can reach by multiplying a vector with x. Okay, and so we know that we have 2 vectors in the span of x down here. So one of them has to be x times alpha, and one of them has to be x times beta hat. Okay, and so it turns out this one over here is x times alpha, and this one over here is x times beta hat. And there really should be an arrow on top of beta hat, but sometimes you drop it because it, gets annoying to write. And so the reason that this specific one over here is x times beta hat, whereas this one over here is x alpha, is because we know from the question that alpha is just some arbitrary vector, whereas beta hat is the optimal value of beta. And what we mean by the optimal value of beta is that it's the one that minimizes the average of all of the residuals. Okay, and so our residual, I guess we can define the residual vector over here, is the difference between our actual predictions our actual outputs y and our predicted outputs y hat. Okay, so in our example, the vector y would be everyone's actual weight, and y hat would be the vector of everyone's predicted weight. Okay, and so the residual y minus y hat is just how wrong we were for each of these predictions on their own. And what we want to do is minimize the L2 norm squared of our residuals. And this looks like the sum of the squares of all of our residuals. And so sometimes we put a 1 over n out front. But anyways, this is the same thing as minimizing the L2 norm squared of y minus y hat. But in our case, y minus y hat is just the same thing as y minus x beta hat squared, right? Because y hat, our model is y hat is equal to x times beta hat. Okay? And so the reason I know this one over here is x times beta hat is because I know that my prediction y hat, which is what this over here is a projection of y onto the column space of x. Okay, and the reason that that's the case is because that's how I make my prediction y hat be as close to the value of y as possible. Right? I know whatever I predict has to be in the span of x, and so in order for it to be as close to y as possible, so in order for my residuals to be as small as possible, what I do is project my observation vector y into the column space of x. And the reason I know that this one over here is the projection is because it looks like this residual is orthogonal to the span of x. And that's a property we will rely on in subsequent questions. Okay, you can see, you can think about this visually perhaps. If I took this vector over here, x times beta hat, and made it point anywhere else, this residual vector over here, first of all, would no longer be orthogonal to the span of x, but it would also be longer, right? If you move this vector really in any direction, it would increase the length of that vertical residual vector. And we want the length of that residual vector to be as short as possible. And so in order to do that, the residual vector needs to be orthogonal to the span of x. Okay, and so that was pretty quick, and we just covered all of these terms over here. But hopefully that explains why this box is x times beta hat. This over here is y because it's our actual observation vector, so the vector of everyone's actual weight, and this is our residual, i.e. how wrong we were, y minus x beta hat. Cool, so that is us filling in this diagram. Now let's interpret this diagram in the form of questions 2, 3, 4, and 5. So in 2, we want to use the figure above to explain why for all alpha in RP, and this should really say alpha with a vector arrow on top of it in RP, that the L2 norm squared of y minus x alpha is greater than or equal to the L2 norm squared of y minus x beta hat. And so to be precise, there should be subscripts 2 here, though sometimes we omit those, and there should be vector hats over here. We sort of already talked about this idea, right? We chose beta hat so that it minimizes the norm of our residual, right? We chose beta hat in order to minimize the L2 norm of this residual. So if we replace beta hat with any other vector, we know the residual will no longer be minimized. Okay, so the minimum value of the residual comes when we put our optimal value of beta in for the vector we multiply x by. If we replace beta hat with any other vector, the size of the residual is no longer minimized. Okay, so there's not much for me to write down for that. We sort of already discussed this idea. So maybe I can say beta hat minimizes the residual. So this is almost sort of by definition. 3, from the figure above, what can we say about the residuals in the column space of X? Express your statement using linear algebra ideas. Well, I sort of also already mentioned this, but it's that in order for our residuals to be minimized, they need to be orthogonal to the column space of X. Okay, so I can say explicitly the residuals are orthogonal to the column space of X. And one thing I should note is that I've been using the column space of X and the span of X interchangeably. Well, that's because they're the same thing. The column space of X, span of X mean the exact same thing. To span of X. Okay? And so now the question is, how can I express this perhaps more symbolically? And this is what we will need moving into question 4. Well, I know my residual is y minus x beta hat, and again, those should have vectors on them. And the span of X, well, that's sort of made up of, it's the span of this set of p column vectors. And in our example, p is 3, but in general, I have, just p column vectors, and I'm saying my residuals need to be orthogonal to all of them. Okay, and so again, maybe to remind ourselves, I can write X as a series of column vectors, and I'll go all the way till p because we typically have p features. I want my residuals to be orthogonal to every single one of these vectors in the span of X. Okay, so what I could say is that the dot product of x1 and y minus x beta hat should be 0. The dot product of x2 and y minus x beta hat should be 0, and so on and so forth, all the way until xp. All of these dot products should be 0. One thing to note here is that over here, underlined in red, this is X the matrix. Whereas what I'm underlining now with the vector hats, those are vectors corresponding to the columns in X. So what I've now addressed is the idea that my residuals need to be orthogonal to each of the vectors that make up the columns of X. Okay, and how do I say two vectors are orthogonal? Well, it's by saying that their dot product is 0. Another way to express the fact that two vectors are orthogonal, i.e. another way to express that the dot product is 0, is by saying one vector transpose the other is equal to 0. Okay, this is a perfectly equivalent way to express the dot product between two vectors. And so in question 3, for each of my p vectors, I individually wrote out these dot products. I could also individually rewrite them out again using one transpose another, but we need something a little more general, okay? And it turns out instead of writing p individual statements, one for each column vector, I can actually summarize this into a single statement, which is just that X as a whole is orthogonal to y minus x beta hat. Okay? Notice that there's no vector arrow on top of this because now I'm talking about the entire matrix, whereas over here and over here and over here, I was talking about each of the column vectors in X. I'm now looking at X as a matrix as a whole. And so this statement that I've written over here really encapsulates the p individual statements that I was writing in question 3. So this is saying that all of the columns in X are orthogonal to the residual vector. Okay, and so now what this wants us to do in question 4 is derive that X transpose Y is equal to X transpose X beta hat. Okay, and we can actually take this one step further and derive the optimal solution for beta hat here in this question. How can I do that? Well, I can distribute the multiplication of X transpose on the left to get X transpose Y minus X transpose X beta hat is equal to 0. Then I can add this second term to both sides of my expression. And I'll do that just by moving the equal sign over here to save space. So now I have X transpose Y is equal to X transpose X beta hat, as the question wanted me to derive. But again, we'll go one step further. And to isolate for beta hat, what I can do is multiply both sides of this expression by the inverse of X transpose X. Okay, so I get that X transpose X's inverse times X transpose Y is equal to X transpose X's inverse times X transpose X beta hat. Now what happens? Well, X transpose X's inverse times X transpose X, those cancel out and I'm left with beta hat. And so this, just switching the left and right sides of the equal sign, I get that beta hat is equal to X transpose X inverse X transpose Y, as we've seen in lecture. Okay, so to recap how exactly we got to this solution, we made the observation that in order for our residuals to be minimized, they need to be orthogonal to the span or column space of X. That gives me that X transpose, my residuals, must be 0. Then I expanded out this multiplication and multiplied both sides by X transpose X's inverse, and I got this solution to the normal equation, which hopefully by now is familiar. Okay, and so again, for clarity, let me rewrite this again. X transpose X inverse X transpose Y. In question 5, we're told what must be true in order for this solution to actually exist, because it doesn't always exist. Okay, what must be true about X in order for this thing to exist? Well, you see here, this solution relies on X transpose X being invertible. Okay, so we need X transpose X to be invertible. Okay? Well, another way of expressing the condition that a matrix is invertible is by saying that it's full rank, i.e. all of its columns are linearly independent. Okay, so this is equivalent to saying that X transpose X is full rank. Okay? To take this one step further, we didn't really prove this in class, and we're not going to prove it in this discussion either, but it's a fact, and you can take it as being a fact, that the rank of X and the rank of X transpose X are the same quantity. They're always equal. Okay? And you can do this by showing that their null space also have the same rank, and then by the rank nullity theorem, you can show that their ranks are the same. But again, that's not that important for our purposes. I know that X transpose X and X have the same rank, so that means if X transpose X has to be full rank, well, that means X has to be full rank. And so that is really the assumption, that's the condition we need in order for this solution to the normal equation to exist. We need X to be full rank. And so that means all columns of X need to be linearly independent. Because if they're not, well then X won't be full rank, and then you can't invert X transpose X. Okay, another property that needs to be true for X to be full rank is that we need there to be more rows than columns. Or like the number of rows has to be greater than or equal to the number of columns. Because if we have more columns than we have rows, our matrix will be extremely wide. I mean, this is not really an exact picture, but you get the idea. Our matrix will be really wide, and this comes from the fact that the rank of the column space and the rank of the row space of a matrix, are the same. So the rank of the column space, rank of the row space are the same. And so clearly here, suppose we only have 3 rows and 10 columns, for example, the maximum value of the rank of the column space will be 3, right? Because there's only 3 things in each column. And so the maximum value of the column space will be 3, and 3 is not equal to the number of vectors in X, right? Because there would be 10 vectors if I had 10 features. And so I need there to be more rows than we have columns. Okay? And, put in terms of the data perspective, I need there to be more observations than features. Okay, so rows are observations, columns are features. But granted that these two things hold, then x will be full rank, and so the solution to the normal equation will exist. And so I think that wraps up the first half of the discussion worksheet on the geometry of least squares. Great. Now the second part of the worksheet is on one-hot encoding or dummy variables. Okay, and just as a quick refresher, one-hot encoding is the process of taking some feature that is made up of, so some feature that's categorical, and transforming it into being numerical. Okay, so for here, our example is we have this one variable that takes on the values a, b, and c. Of course, those aren't numbers, so we can't just put them in our data matrix and do calculations with them. We need to somehow turn them into numbers. And what we will do is create 3 new columns in our data matrix, one corresponding to a, one corresponding to b, and one corresponding to c. And so how it works is for each row, exactly one of the columns is equal to 1, and the other 2 columns are equal to 0. So for instance, in the first row, we have a 1 in the A column because the first observation was a 1. In the 5th row, we have a 1 in the B column and zeros everywhere else because the 5th observation was a B, and so on and so forth. And I think it's pretty easy to see the pattern, right? We have 4 straight A's and 3 straight B's, 3 straight C's, and that's just a formulation of what we're given in the problem. Okay, and so in this question, we will be doing some manipulation with this data matrix X. So to be explicit, this is what we're going to refer to as X. And yeah, let's get into it. So really quickly, before we do that, it's important to note that the 3 columns of my data matrix, we will call XA, XB, and XC. So this column will be XA, this will be XB, and the last one will be XC. Also, it's worth noting that while the question doesn't state it, we kind of need the fact that there is a y vector which contains all of our true observations. We don't really know if there's a real world example for what y's are, but we need to know that they exist. Okay, in problem 6, we're told to show that the columns of X are orthogonal, i.e. the dot product between any pair of columns is equal to 0. And so an intuitive way to see that is by looking at the matrix and realizing that for each row, there's a 1 in exactly one of the columns, and both of the other columns is equal to 0. So if I pick any 2 of these columns, so for example, if I look at the first and second, and I look at each row, one of those elements will be a 0, at least one of them. And if you look at the bottom ones, they're both 0. And so when I take the dot product between of these 2 columns, each term will either look like 1 times 0, like it does here, right? Or 0 times 1, as it does for the b values, or 0 times 0. So each term in my dot product looks like 1 times 0, 0 times 1, or 0 times 0. But we know that 0 times anything is just equal to 0. So that means every term in my sum, when I'm computing the dot product, is just equal to 0. So if we want to be a little more explicit in the case for the first 2 vectors, right, and this really generalizes for any of the 3 pairs of vectors we take, I could say, the dot product of XA and XB, well, 4 times I have the value 1 times 0, 3 times I have the value 0 times 1, and 3 times I have the value 0 times 0. All 3 of these things are equal to 0, so I just have 0 plus 0 plus 0, which gives me 0. Okay, so if I pick any 2 columns, take the dot product, since in that dot product, each of those sums will be equal to 0, my result is also 0. In 7, what I want to do is show that X transpose X is this diagonal matrix where the elements in the diagonal are the number of elements belonging to class A, class B, and class C, or number of observations, I should say. So in our specific example, this looks something like 4, 3, and 3 with zeros everywhere else, okay, because there were 4 observations belonging to class A, 3 to B, and 3 to C. Okay, and so actually to make question 7 and 8 easier, I pre-wrote out what the multiplication of X transpose X looks like. Okay, so over here I have X transpose, over here I have X. And just to remind ourselves, the columns in X are called XA, XB, and XC with their arrows. And over here, since X transpose, I just took the columns of X and turned them into rows. I have XA transpose, XB transpose, and XC transpose. Okay, so the first key observation to make is that when you look at X transpose X, it's actually a matrix of dot products. Okay, and so sometimes X transpose X generally is referred to as an inner product matrix. Well, why is that the case? Well, let's see. We know, from the question that there are going to be 9 elements, or like X transpose X will have 9 things in it. The top left element of X transpose X will be the result of multiplying the first column in X with the first row of X transpose X. Okay, so I take the first column of XA, or the first column of X, which is XA, rotate it, dot product it with the first row of X transpose. Well, that just looks like XA transpose XA. The second element in the first column will be the result of doing the same thing, but instead starting with XB, right? So I'll have XB transpose XA. And the next thing will be XC transpose XA. Okay, and I can fill in my matrix accordingly. The result of each of these things is just a dot product. Shouldn't be a transpose there. And lastly, XC transpose XC. The reason I'm not going to fill in everything else is because they're all 0. Because as we saw in question 6 over here, the dot product of any 2 columns is equal to 0. And we should have been slightly a little more specific than we really meant the dot product of any 2 not equal columns. Okay, so if I just pick 2 different columns, take their dot product, it's going to be equal to 0. Everything other than the elements of the diagonal in X transpose X is just the dot product of 2 unequal columns. Okay, right? So for example, here I'd have XB transpose XC, for instance. That's also going to be equal to 0. And so all of these elements that are not on the diagonal, I can just replace with the 0 because they're the dot product of 2 not equal columns. And so now all that's left for me to figure out are the elements on the diagonal of this matrix. And so for instance, if I look at XA transpose XA, i.e. the dot product of XA with itself, that's the sum. If I, think about this as rotating XA and writing it over here, it's the sum 1 squared plus 1 squared plus 1 squared plus 1 squared plus 6 0 squareds. Right? Dot product of a vector with itself is the sum of the squares of the elements in that vector. 1 squared is just 1, 0 squared is just 0. So this is just the number of elements in that vector that were equal to 1, which in this case was 4. But more generally, it's just equal to the number of elements in that vector that were equal to 1, right? So that gives us this definition of NA, NB, and NC as we saw before, right? If you want to visualize it again, for NC, let's say, maybe pick a different color, like, orange. That would be taking the dot product of this column with this row, so the dot product of XC with itself. The first 7 terms in that sum would just be 0 squared, and the last 3 terms would be 1 squared plus 1 squared plus 1 squared, which gives me 3. Okay? All of the other elements in this matrix are 0, as we identified, and so on the diagonal, we just have the number of observations that belong to class A, class B, and class C as required. In problem 8 now, very related, what we want to do is show that X transpose Y is equal to a vector with 3 elements, the first element being the sum of the Y values for the observations that belong to class A, the second element being the sum of the Y values belonging to class B, and lastly, the sum of the Y values of the elements belonging to class C. So if we quickly switch back over here, essentially what this is asking us to show is that X transpose Y, the first element in that vector is equal to the sum of Y1 through Y4. The second element in that vector should be the sum of Y5 through Y7. And the third element in that vector should be the sum Y8 through Y10. Okay, and so the reasoning for this is very similar to the reasoning behind X transpose X, right? What I'm going to do to compute the value of X transpose Y is take this column vector y, rotate it, and dot product it with each of the rows in X transpose. So for instance, the first row will look something like 1 times y1 plus 1 times y2 plus 1 times y3 plus 1 times y4 plus a bunch of zeros for the remainder of my sum. Right? 0 times y5 through y10 still just gives me 0. So I'll have 6 terms. They'll all be equal to 0. We're not going to write them all out. But I think it's clear that all of those things should be equal to 0. Now, for the second element in X transpose y, I will take the dot product of my y vector once again, but now instead just with the second row of X transpose, right? And so y1 through y4 get multiplied by zeros, so they're not included in the sum. y5, 6, and 7 correspond to 1s over here, and so I'm left over here with 1 times y5 plus 1 times y6 plus 1 times y7. And I guess for clarity, we can show that there's a 0 in the beginning. And then after it, y8, 9, and 10 correspond to zeros once again, so I have a 0. And then lastly, for the third element in X transpose y, everything except for the last 3 get multiplied by a 0. The last 3 in this case are just 1 times y8 plus 1 times y9 plus 1 times y10 and a bunch of zeros before that. Okay, so in this case, X transpose y simplifies to y1 plus y2 plus y3 plus y4. Second element, y5 plus y6 plus y7. And third element, y8 plus y9 plus y10. Okay? It's important to note that this is a vector, a column vector with 3 elements, and not a matrix or anything like that. And we can clean up the notation we have here to be a little more general. We know y1 through y4 were just the y's that belonged to class A. So I guess we could say, I belongs to class A of yi. The second element was where I belonged to class B. And the third element would be where I was in class C. Is that the same notation they use? Yeah, it is. Okay, so the result of multiplying X transpose by Y is a vector with 3 elements where the 3 elements are the sums of the Y values corresponding to the 3 classes we had, A, B, and C. And the result of that becomes clear by writing out this multiplication as we've done. Now lastly, in question 9, I'll rewrite it over here for clarity. We want to use the normal equations, which as we looked at earlier in this video, the solution for beta hat is X transpose X inverse X transpose Y. What we want to do is show that in our case, this is equal to YA bar, YB bar, and YC bar. Okay, i.e. the average value, the average Y value for when the class is equal to A, the average Y value when the class is equal to B, and the average Y value when the class was equal to C. And so we don't need to work from scratch. We already know what X transpose Y is from the previous question, right? And we already know what X transpose X is from question 7. All we need to do now is find the inverse of X transpose X and multiply that by X transpose Y. Okay, so we know X transpose X is this diagonal matrix NA, NB, and NC. And so now the question is, what is the inverse of X transpose X? Well, it turns out the inverse of a diagonal square matrix is just another diagonal square matrix where all of the elements on the diagonal are replaced with their residuals. And so in our case, what that means is that X transpose X is actually just equal to 1 over NA, 1 over NB, and 1 over NC on the diagonals, and zeros everywhere else. Okay? We won't go through the process of showing this in this video, but you can prove to yourself that this is indeed the inverse of X transpose X by writing out the product of X transpose X with this inverse, and you'll get back the identity matrix. Okay? So the inverse of X transpose X is this new diagonal matrix with 1 over NA, 1 over NB, and 1 over NC. And you can sort of see why that's the case, because when you multiply this by this, you get NA times 1 over NA, which is 1, which sort of makes sense, right? Because the top left element in the identity matrix should be a 1. But anyways, we have x transpose x now. All we need to do is multiply this quantity by x transpose y. So let's do that. So beta hat now, x transpose x inverse x transpose y, which looks like this thing again, 1 over NA, 0, 0, 1 over NB, and 1 over NC, multiplied by, let's just copy this. Oops. Cool. Paste that over here. Nice. Cool. And so now the result of doing this matrix vector operation is just another vector, right? Because when I take this vector, rotate it to do my multiplication, at least for the first row, the second and third sums get multiplied by 0, and so they drop out. And so the same thing that's been happening occurs again, where you only really multiply by the relevant classes. And so what I mean by that is that the first row of this multiplication will look like 1 over NA times the sum when I was in A of yi. The second row would be 1 over NB times the same thing for B. And the third row is 1 over NC times the same thing for C. So now I have that beta hat is equal to the sum of all of the y values belonging to a certain class, A, B, or C, divided by the number of observations belonging to that single class, right? So a sum divided by a number of observations, we've seen this time and time again as being the mean. Okay, so this is really a vector of 3 means, ya bar, yb bar, and yc bar, where the mean is over all of the observations that belonged to a certain class. So all of the observations whose value is A, the mean of those is ya bar, and similarly for yb bar and yc bar. And we sort of worked up to that by showing individual pieces of the normal equation, right? We started with x transpose x, we then looked at x transpose y, and then finally in question 9, when putting that all together, all we had to do was compute x transpose x's inverse, and then multiply that with x transpose y, which we had already found, and we're given the result we were looking for. So I believe that wraps up the second half of the discussion worksheet, which I believe means we're done with discussion 9. Thanks for watching, and feel free to post on Piazza if you have any questions. And if you're watching this right before you're studying for an exam, good luck.